we want to look at another topic today, that is vectors, lines, planes, and the ratio theorem. But before we dig in, I want to touch a few comments I received over the course of the week. I came to learn we have colleagues who are doing sub-math and they are following these lessons. However, these lessons are tailored for pure math students. That doesn't mean if you're doing sub-math you will not pick something, but there is content which definitely goes a little deeper. And now, whenever I can remember, I will maybe always tell you that this is now not for sub-math, this is for sub-math. But I don't even think I have the whole sub-math syllabus in the head, so sometimes I may forget, or even if I know that the content is not for sub-math, I can still forget. So if you're following these lessons and you're doing sub-math, please, you can try to mail me here so that I can send you the syllabus of sub-math so that you may know what you should consume and what you shouldn't consume. Two, I received a comment. It was saying error 24 over 3 pi is not 6 pi. Yes, that is true. This was the very last answer we had. The last time we met, we were trying to find the volume of a solid of revolution of something. Yeah, the correct thing is 8 what? 8 pi. So I hope you guys corrected that. You know, when you're in the studio and the producers are signaling to you and you're trying to decipher the signals and your brain is locked into a calculation, for a brief moment you may even forget what 1 plus 1 is. So please correct that. The very last thing, 24 over 3 pi, I wrote 6 pi. It's supposed to be 8 what? 8 pi. The very last thing we wrote. Zoom in at the question a little longer. That will be worked on. I guess I have to reduce the speed a little bit. Exercises. Now sometimes it's a bit tricky to write questions here for the exercises. But as we are covering, I anticipate that you guys have textbooks and you can always check there for exercises on a topic that has been covered. Actually, these lessons, these discussions are tailored just to kickstart you off to do personal reading. So you should collect a library of reading materials there so that when something has been taught, you still go back and add on ideas. So from those textbooks and all that kind of thing. So that in those textbooks, that's where you'll meet the exercises. You can use question banks like these popular UNEB question banks and so on and so forth. But once in a while, I could leave an exercise, though it's not always, time is not always with us to write the questions here. The mails. I am responding to a lot of mails. So if there is a delay in the response of your mail, doesn't mean that I've forgotten you. You just have to be a little patient, or you can even send me a reminder. I'm working on most of those mails, and some of you send mails, you want notes. You gotta be specific. What notes do you want, and which topic, and so on and so forth. Now, a number of you are sending questions for help, what you call the hard problems, and in most cases I don't give you the answer direct, but I give you guidelines because I want you to think. I want you to become mathematically independent, be a little bit mathematically independent. So sometimes the answers may not be direct. I can give you steps for the working for the method and so on and so forth. It has worked for a number of you. Some of you send back the mails and you're like, hooray, master, I did it and it came out. And really, that pleases me a lot. So I hope we can keep interacting. You can send in your mails and feedback and all that kind of thing on that mail there. Now today we want to look at another topic that is vectors, lines, planes, and the ratio theorem. For sub-math, there isn't a lot here for you. except that you can stay tuned because you may learn how to solve equations and all that kind of thing. So, what is a vector? We looked at vectors from O-level. Vectors, it's just a quantity with both magnitude and direction and all that kind of thing. We want to skip all that and we go into the things that are going to be required here in our pure math. So we want to look at position vectors. We are basically introducing the 3D vectors. So this point P, it's in space and it has coordinates A, B, C. In other words, you move A units in the X direction, then you move B units in the Y direction, and then you move C units in the Z direction. And so the position vector of the point P is still denoted as OP, and this is, we could write it either in column vector form, that is A, B, C, or the most usual form using the IJK notation, that is A, I, plus B, J, plus C, K. In other words, you move A units in the I direction, then B units in the J direction, and then C units in the K direction, where I is the unit vector in the X direction, J unit vector in the Y direction, and then K, of course, the unit vector in the Z direction. You've met unit vectors, of course, by now. You need to know how to compute the magnitude of the vector OP. That is something you can easily prove. It's A squared plus B squared and then plus C squared. You can use your Pythagoras theorem. The magnitude is basically this length here. So in a time when you're feeling happy, try to prove that actually the length from here to there, for those who enjoyed 3D in O-level, that should be something really extremely easy. Another basic thing we should know is what we call the displacement vector. Displacement vector. Assuming I have 2 points, maybe I have the point A and I have the point B. Maybe this is the point A1, A2, and then A3. And then this is the point B1, B2, B3. So the displacement vector from the point A to the point B is the vector AB. And if we have our origin somewhere, we can just put it somewhere. And then we have the vector OB, and then we have the vector OA, if that is the origin somewhere. You can just put it somewhere. So when you move around that diagram, you realize that to get the displacement AB, this is just the same as you're moving from A to B, that is AO, that is negative of OA, and then plus OB, which we just write as OB minus OA. So to get the displacement AB, you just get the endpoint position vector minus the starting point position vector. And of course, the other thing you also need to know is that AB is equal to negative of BA. These are things which are a bit familiar. You must have done these things a lot, just here to remind you a little bit. Still looking at the basics before we get into the things that are required. We have what we call unit vectors. Unit vectors, you heard me talk about I being the unit vector in the X direction and all that kind of thing. So what's a unit vector? It's just a vector of magnitude 1 unit. The moment you compute the magnitude of a vector and you get 1 unit, then it qualifies to be called a unit vector. So if you have any vector, we can get the unit vector in the direction of that vector using the following computation. So the unit vector in the direction A is, we normally denote it with that notation, a cap. And this is just the same as the vector A divided by the magnitude of the vector A. So using that computation, you can always get a unit vector in the direction of the vector you want. Let's just pick a question, okay? Find the unit vector in the direction of x equals to I minus 2j plus 2k. When the unit vector, so we are looking for x cap, we just need the magnitude of this vector. So in our solution, we'll just say x cap is equal to the vector I minus 2j plus 2k divided by the magnitude of that vector. That's 1 squared plus negative 2 squared and then plus 2 squared. And so this should give us, we have 4 plus 4 plus 1, that's 9. The root of 9 is 3. So the unit vector will be a third I, and then minus 2 over 3j, and then plus 2 over 3k. That will be the unit vector in the direction of that vector there. So we should be able to check that it's a unit vector. Basic D, we have what we call equal vectors. Equal vectors. These are basically vectors with the same magnitude and direction. Vectors the same magnitude and direction. Magnitude and direction. Many of us have made polygons. There are some nice polygons. For example, the parallelogram. If I have a parallelogram, something like that, there is, and we name it maybe A, B, C, and then D. This side is equal in length to this one if it's a parallelogram, and so if we include arrows there, then these guys will have the same direction, meaning that the vector DC should be equal to the vector AB. Why? They're in the same direction and they have the same magnitude. And if we have this, then we would also say the vector AD is equal to the vector BC. So equal vectors. They may have different starting points, but they can be equal. And I will leave you with a question. Question. 3 coordinates of a parallelogram. 3 vertices of a parallelogram. A, B, C, D are A, which is 1, 2, B, which is 5, 4, and C as 1, negative 3. Stop. Find the coordinates. Find the coordinates of point C. And the coordinates of point C. So in our solution, we got ourselves a parallelogram. Well, let this be A, B, C, then D. So the point, find the coordinates of point D. So let point D maybe be x, y, and of course we know these other points here. So find the coordinates of point D. We have two unknowns, which means we need to find two equations to help us get the things we need. So first of all, we shall say that AD is equal to BC. So AD, vector AD is equal to vector BC, but the vector AD is the end point minus the starting point A, 1, 2, and this is going to be the vector BC, the end point. That's 1, negative 3, minus the starting point B, and that is 5, 4. So we basically now have x. X is going to be equal to, we have 1 minus 5, which is negative 4. So this 1 comes the other side. It subtracts, remain with negative 3. And then y, we have this negative 3 minus the 4, which is negative 7. And this 2 comes the other side. Negative 7 plus 2 is negative 5. And so D is the point negative 3, negative 5. So we now have a good idea about what equal vectors are. E, we have what we call parallel vectors. So if A is parallel to B, then there is a scalar. That's scalar and a constant such that A is a scalar multiple of B. So if two vectors are parallel, then we say they are scalar multiples. If they are parallel, then they are scalar multiples. We can use that property to prove that 3 points are collinear. For example, nota bene, to prove that points A, B, and C are collinear, that is, they lie on a straight line. It is enough to prove that the vector AB is parallel to the vector BC. So we get something of this kind. If they are on a straight line, this is the point A, this is the point B, a common point, and this is the point C. If they are to be parallel, then this must be parallel to that. Otherwise, if BC is not if C was at a different point there maybe, then they wouldn't be collinear. That is, AB wouldn't be parallel to BC. So the moment this is parallel to that, then we conclude that they are collinear. That is, they lie on the same straight point, the same straight line. So I'll give you a question. In other words, the moment you can find such a scalar, and you have a common point here, then they are collinear. So let me give you a question you can try out when you are in a nice mood. If given the points, I have the point A, and this point is 1, -2, -2, 2. B is 3, 2, -1. And C, given the points, that, and C, which is 7, 10, -7, comma, prove that A, B, and C are collinear. Prove that A, B, and C are collinear. You will try out that in a time when you're feeling happy. Another basic concept that we need to know if we are going to be talking about vectors is something to do with multiplication of vectors, and that's what we call the dot. This is F, the dot. Sometimes it's called the scalar, the dot, or the scalar product, the dot product, or what we call the scalar product. So what is this guy, or who is this guy whom we are calling the dot product? So let theta be the angle between A and B. Then we define the scalar product. We denote and define the scalar product of A and B as A dot B, and this one is given by the formula magnitude of A times magnitude of B times the cosine of theta. Remember, theta is the angle between the two vectors. That is how we denote, this is how we denote the scalar product, the dot product of vectors A and B, and that is how we define it. So you can say this is a real number, a real number, a real number. So when you multiply real numbers, you're going to get a real number. So A dot B is a scalar. That's why they even call it a scalar product. It's not a vector. So when you multiply two vectors via the dot product, you're going to get a real number and not a vector. We have another definition depending on how A and B have been given. Now, if A is given as A1, A2, and then A3 in 3 dimensions, and maybe the vector B is B1, B2, these are subscripts, B3, then again we can define A dot B as A1, B1 plus A2, B2 plus A3, B3. That is the sum of products of corresponding components, the sum of the products of corresponding components. You can give yourself a task, try to move from this way and prove to this way, or try to move from this one, move to that way. That can be a very good exercise for your brain. Try, do it really. It will help you to think, to develop your thinking skills when it comes to mathematics. Remember, in mathematics, we are basically targeting to stimulate thinking, to stimulate thought processes. Let's look at a few of properties of the dot product, because you might meet it somewhere and you may need to apply these properties. So one, A dot B is 0 if A and B are perpendicular. This is a bit trivial. You can see it directly from the definition here. We know that when A is perpendicular to B, then the angle between them is 90, and the cosine of 90 is 0. So we'll have 0 times some other two numbers giving us 0. So the moment two vectors are perpendicular, then their dot product is 0. 2, we have commutativity. A dot B is B dot A. We call that commutativity. You can try to prove that. Give yourself time. You can try to prove some of these properties. And then 3, we have distributive property. That is A dot B plus C. That when you dot the vector A with the vector B plus C, this is just the same as dotting A with B, and then you add the dot product of A and C. This property is similar to a property of real numbers you guys are very familiar with. It is a bit similar. We call this the distributive property, right distribution, distributive property. Sometimes the dot product behaves like that. This property, some of you have tried to prove the cosine rule via vector methods. You needed that property to be able to do that, and this one here. Then one more property, that is, if I get the vector lambda A, where lambda is a scalar, and I dot it with B, this is just getting lambda, and I multiply it with the scalar product of A and B. Each of these are so easy to prove. You can prove them. None of them is really hard. They're so easy to prove. So as you're writing, you can jot somewhere required to prove, and when you have time, you can prove some of those. Let's pick something like an example. If A is the vector 2i plus 2j and then plus k, and B is the vector 3i plus 4j and then plus 12k. Find the angle. Find the angle between A and B. And to find the angle between those two vectors. So we are going to apply definition of the dot product. In that definition, we need the magnitude of A, we need the magnitude of B, we need A dot B. So we shall find these. So A dot B is going to be, we are dotting 2, 2, 1 with 3, 4, 12. And by the definition, we are going to have 6 and then plus 8, that is 14, and then 14 plus 12, that's 26. So the dot product is 26. Be very careful not just to multiply like that and leave. You multiply while adding according to the definition. You get this times this plus this times this plus this times that. Then now the magnitude of A, this is going to be the square root of 2 squared plus 2 squared plus 1 squared. This is 4 plus 4 plus 1, 9, root 9 is 3. And then magnitude of B, this is going to be square root of 3 squared plus 4 squared and then plus 12 squared. So we have 144 plus 25, which is 169. Root of 169, that's something like 13. And so from there now we can find the angle. We define the angle. Sometimes mathematics students don't want to define the angles. So let theta be the angle between A and B, so that we may know what you're finding. At times, before you find one angle, you may need to find another angle, and when you've not defined things, things can really be, the working may not really be so nice. So try to always define those things. So we know that A dot B is equal to, we know from the formula that A dot B is magnitude of A times magnitude of B, and then cos of theta. So that means that theta should be the cos inverse of A dot B, that is if you make theta the subject, over magnitude of A times magnitude of B. And so we shall say, let theta be the angle between A and B, then theta is going to be equal to the cos inverse of 26 over 3 times 13. So that is something like the cos inverse of 2 over 3. So we employ the services of a calculator. Shift cos inverse of 2 over 3, and that will give us something like 48.19 degrees. That is rounded off to 2 decimal places. We are still looking at the basics, things you should know before you begin delving in to understand vectors. Speak another question as we prepare ourselves. Now, if 2 plus alpha j plus alpha k is perpendicular to negative alpha, this is I minus k, find the value of alpha. Find the value of alpha. Okay. So we are told that two vectors are perpendicular. That means their dot product must be 0. And so we shall say 2 alpha alpha dot, this is going to be equal to negative alpha. The component in the z direction is 0. And then this is negative 1. That should give you 0. Not the 0 vector, but the 0, the scalar. And so we shall have negative 2 alpha minus alpha, negative 2 alpha minus alpha. Let me see. This is my question fine. 2 alpha alpha, then negative alpha. Okay, we have negative 2 alpha. Whatever is coming out is what we shall take. And then, oh, this was a 2. This was a 2. This was a 2. Please correct that. And so, negative 2 alpha, and then minus 2. Minus 2 is equal to 0, which of course means that alpha is going to be negative 1. Alpha will be negative 1. So that's a 2. Please correct that. Another thing you need to know is how to use the dot product to find a vector which is perpendicular to some 2 vectors. Find a vector perpendicular. Find a vector perpendicular to A, which is the vector 1 to 1, which is perpendicular to both A, that, and B, which is 3 to negative 1. 3 to negative 1. So in our solution, let the vector be n. So we want a vector which is normal to A, but at the same time it is also normal to B. That is always possible in real life. For example, if we have the vector, this is the J, and then we have the vector K, the anti-vector in that direction, you realize that the vector here, I, is perpendicular to that, and at the same time it's perpendicular to that. So it's possible to find a vector which is perpendicular to two other vectors. So in this case, we shall let the vector be n, and let's give it some components here, n, a, b, c. So we know that a dot n is equal to 0. A dot n is equal to 0, and this means that 1 to 1 times ABC is 0, which would mean that A plus 2B plus C, that is A plus 2B plus C, is 0. We could call that equation 1. Then we also know that B dot n is also 0, which means that we have 3 to negative 1 dot ABC is equal to 0, and this means that 3A plus 2B, 3A plus 2B, and then minus C is equal to 0. We'd call this equation 2. Now we have 3 unknowns and 2 equations. So it means we are going to get a solution set. We are going to get an infinitely, the solution to that system is not unique. It's not unique. So what we will do, we shall first of all set, maybe we can say, let's C equals to K. Then we have that A plus 2B is going to give us negative K. And then we also have that 3A plus 2B is going to give us K. We could call this 3, we could call this 4. So we want to solve, we want to find A and B, each of them in terms of K. What we could do, we could eliminate B by getting equation 3. We subtract equation 4, which would mean that negative 2A is going to be, this is negative 2K, which means that A is going to be subtracting negative K minus that, okay? So A minus 3A, that's fine. So A will be 1. A will be K. And then if we want to get B, we shall substitute in here. So we know in 2, 3, we can say K plus 2B is equal to negative K, which means that B alone is going to be, this goes the other side, becomes negative 2, so B alone is going to be negative K. Because when this goes, we have negative 2K, divide both sides by 2, you remain with negative K. So therefore, the vector n is going to be equal to, we have A, which is K, B, which is negative K, and then C, which was K. And this we could factorize out k, and then we have 1, -1, and then 1. So this means that any vector which is parallel to this vector is normal to the other two guys. So if we let k be 1, you can choose any value of k, then we can have n to be equal to 1, -1, 1. So that would be a normal vector to those other two guys there. So you can pick any value of k, because we are seeing that anything parallel to this is perpendicular to the other two vectors. Okay, now there is something a little sensitive I'm going to touch here. We normally use, I've met a question requiring one to prove that 3 points form vertices of a triangle. Nota bene. To prove that 3 distinct points, to prove that 3 distinct points A, B, and C form vertices of a triangle, it is enough to prove that. I have seen some few textbooks which many of you guys are reading, and the formula there is that if I want to prove that those 3 points form the vertices of a triangle, that I should prove that AB plus BC plus CD, AB, we have something like ABC. So plus AC, AB plus BC, and then plus CA. That is equal to 0. I've seen a number of textbooks with that. However, this does not prove that those are vertices of a triangle, because this also holds for collinear points. If A, B, and C are collinear, go try and check. You'll see that it is also satisfied. You get AB, that is, you're starting from A. So get AB, then plus BC, then plus CA. You get back the original position. But this guy is not a triangle. So when you find this, it's not conclusive. It's not conclusive in itself. It doesn't prove that they are vertices of a triangle. To prove that these are vertices of a triangle, that means you must rule out the collinearity possibility. That is, these points should not be collinear. The moment they are not collinear, then we got ourselves a triangle. And how can you prove that they are not collinear? How can you prove that they are linearly independent? There are a number of ways you can do that. First of all, you can prove that at least one of these angles is not 0 or is not 180. So it is enough to prove that maybe AB dot BC is not positive or -1. You can prove that. You would have proved that they are not lying on a straight line. So not all of them are lying on the same straight line. So it's a triangle. Or you can prove, how do we call it, the triangle inequality. You can prove that maybe the vector AB is less or equal to BC. The sum of two sides, of the lengths of two sides, is always smaller than one side. The length of one side cannot be bigger than the sum of the lengths of the other two sides. How do you write that? The vector AB should be less than BC, should be less than, in fact, strict less than BC, and then BC, and then plus SC. That's another way you could prove that they form vertices of a triangle. Or you can prove or you can prove that the area of triangle ABC is not 0. Yeah, if you can prove any one of those, that should be enough to show that you are dealing with vertices of a triangle. Otherwise, just moving around that thing does not really prove that it's a triangle. It doesn't really prove that. Okay, so I'll leave you with a question. Prove that. So in other words, all you're doing here is you're proving that the points A, B, and C are linearly independent. They don't lie on the same straight line. The moment they don't lie on the same in other words, you are proving that they are not collinear. So the moment they don't lie on the same straight line, there is always a triangle that can be drawn such that they are vertices of that triangle. So prove that A, which is 2, 3, negative 1, B, which is negative 3, 4, 6, and C, which is 4, 3, 5, 4, 3, 5, are vertices of a triangle. Vertices of a triangle. So since we are dealing with the dot product, you can try to prove that this guy is different from positive or negative 1. And that will be enough. That would be a sufficient condition to prove that these guys here are vertices of some triangle. So you can do that in a time when you are happy with yourself and you're not feeling really confused. G, another product of vectors is what we call the cross product. The cross product. Sometimes they call it the vector product. The cross or vector product. Cross or vector product. So again, we shall let n be a unit vector perpendicular to A and B, perpendicular to both A and B, and let theta be the angle between A and B. Then, so we want to define the cross product. Another definition of a product of vectors. So we define A cross B, that's how we denote it, as the magnitude of A times the magnitude of B times the sine of the angle between the two vectors, and then times the unit vector in the direction perpendicular to each of those two guys. So I want you to notice the difference now between the dot product and the scalar product. The scalar product, it's a number, it's a value, a real number. However, the cross product is a vector. Cross product is a vector, and its magnitude is this. This is its magnitude. So the cross product, you end up with a vector. We have another definition. That is, if, of course, A is given by A1, A2, A3, and B is B1, B2, B3, then we can define A cross B to be the determinant of this 3 by 3 matrix, that is I, J, K, and then we have A1, A2, A3, and then B1, B2, B3, the determinant of that matrix there. And how do we compute the determinant of that matrix? Of course, we use cofactors. We will, first of all, if we want to get the ith component, we remove this, the row and the column containing I, and then we get that. So this is just A2, B2, A3, B3, I, then minus. We come to this, we remove this and that, we remain with A1, B1, then A3, B3, the determinant of that, that's the jth component, and then plus, we remove this and this, we have A1, B1, A1, B1, A2, B2, and that's the component in the K direction. Okay. We will also look at some properties. We'll look at some properties of the cross product. You may need to use some of these properties of the cross product. And in the interest of time, that is where we shall begin from next time. Thank you for staying with us. Have a good evening.
Somera mu ddiiro lyo ng'ewagiddwa Merryland High School erisangibwa Entebbe. Somero lya bawala n'abato